Hey everyone, welcome back, and let's write some more leetcode today. So today let's solve the problem balanced binary tree. We're given a binary tree and we want to determine if it is height balanced. What exactly do they mean by height balanced? Well, it's defined by saying that for every single node in the tree, if we take the left and right subtrees of this node, the heights of these left and right subtrees will differ by at most 1. So in here you can see, taking a look at the root node, it has a left subtree. What's the height of this left subtree? Let's call it 1, right? Because there's one node in the left subtree. What about the right subtree? What's the height of this right subtree? Well, it's 2, right? We can determine that just by looking at it. So then the left subtree has a height of 1, the right subtree has a height of 2. The difference is at most 1, right? Because if we take the absolute value of the difference, we get 1. So we'll say the difference is 1. So we just did that for the root node, but we have to do that for every single node to make sure that the left and right subtrees of every single node differ by at most 1. And just to show you a counter example, so this is kind of a badly drawn tree, but take a look at the root node, right? If we take a look at the left tree over here, the height is 3. If we take a look at the right subtree, the height is 3. So the difference is 0, which fits into our criteria. So from the root node, the left subtree and the right subtree are balanced. But if we take a look at, let's say, this node, right? We take a look at its left subtree, which is empty, right? So that has a height of 0. The right subtree has a height of 2. So in that case, the difference is 2 minus 0, which is 2, right? Positive 2, which is greater than 1. So just because from here, taking a look at the root node, the left and right subtrees are balanced, doesn't mean that that's going to be true for every single node, because we just looked at this node, the left and right subtrees were not balanced. How can we solve this efficiently? Let me first show you kind of a naive approach, and then we'll see how we can actually optimize that. So if we were asking naively, right, the first question we're asking is, from the root node, are the left and right subtrees balanced? How do we even determine that? Well, do you agree that we could probably do a recursive DFS on the left subtree to determine the height of the left subtree, do a recursive DFS on the right subtree to determine the height of this subtree, and then we could compare those and make sure that the difference is less than or equal to 1. Do you agree that we could do that? Probably, right? I'll explain more details in the code, but for now, let's just assume we can do that. We start from the root, we run a DFS on the left and on the right. That means we go through every single node in the tree. So we just did an O of n operation, right? And we were able to determine, okay, from the root node, yes, it is balanced, but we're not done yet, right? Now we have to continue to ask that question for every single node, right? So the next question we're going to ask is, suppose on the left subtree, right? From the left subtree, are the left and right subtrees from this node also balanced? And of course, they're both 0, so we determine that they are. And then we'll have to recursively go to the right subtree. From here, we're going to ask, are the left and right subtrees balanced? Yes, they are, but we'll recursively have to continue. We'll have to do that from this node, and then we'll have to do that from this node. Since we're running a recursive DFS on every single subtree on this root tree, we're going to have to do basically an O of n operation each time we ask that question. Is it balanced from here? Is it balanced from here? Is it balanced from here? And we could have a really big tree, and we'd have to do an O of n operation each time. O of n is the number of nodes in the tree, and if we have to do this n operation n times, we're going to get a time complexity of O of n squared. So now the question is, can we do better than that? Is there any repeated work? And I'll show you that yes, there is repeated work, and it basically can be eliminated by asking the question in a different order. What I mean by that is instead of first asking if the entire tree is balanced from the root node, right? That's the first question we asked. Is it balanced starting from here? Instead of asking that, we do this bottom up. We recursively, instead of asking it from here, we're going to check, okay, is this entire right subtree balanced? Before we do that, we're going to ask, is this entire subtree balanced? And we're going to keep going lower and lower until we get to the base case. Once we get to the base case, then we're going to go back up, and I'll show you how that's actually going to end up eliminating the repeated work. If we do it in this order, we'll only have to visit each node at most one time, which will ensure the overall time complexity is going to be big O of n rather than n squared. Okay, so when we get to the root, before we check if it's balanced from here, we're going to check if it's balanced from this right subtree. That makes sense so far. And then before we ask from this position, we're going to ask, is it balanced from this leaf node, right? And now we can't really go any lower because this node doesn't actually have any children. So of course its subtrees are going to be balanced, but now we're good, right? We determine, okay, from this node, yes, the left and right subtrees are balanced, right? And then we pop back up, suppose, and then we also want to make sure that this node is also balanced. It's the same thing, right? The left and right childs don't exist. So yeah, it's balanced from here as well. So we determined that, right? Now we know from at least these two nodes, yes, the left and right subtrees are balanced from these two nodes. Okay, now we want to know, is it balanced from this node? How can we determine that? Aren't we going to have to go back down and revisit the entire right subtree and the entire left subtree again? No, and I'll show you why. As we are determining if this subtree is balanced, let's also at the same time, simultaneously, let's make sure we get the height of this tree, the entire height of this subtree, and let's do the exact same thing for this node. Make sure we get the entire height of this subtree, because once we've done that, then once we go back up to the parent node from here, it will be easy. We already have the height of this tree. We already have the height of this tree. We can take the difference between those, make sure it's less than or equal to 1, and then we're good. We didn't even have to revisit these trees, right? From this node, now we've already determined, yes, it's also balanced from this position, right? So now we've determined it's balanced from this node, balanced from here, and balanced from here. And now we want to go back up to the root node and make sure it's balanced from here. Before we do that, we have to solve the subproblem on this left subtree. It's just a base case problem, right? It's just a single node, so we know it's balanced from here as well. So now we want to go back up to the root node. Is it balanced from this root node? Well, as we are doing this, right? As we were doing this right subtree, we determined that the height of this tree was 1. The height of this tree was also 1, right? So now we want to know before from this node over here, before we return back up to the parent, we want to know what's the entire height of this subtree. How can we easily determine that? Well, we know that this was 1. This was also 1. So from here, the height is just going to be 1, meaning this 1 comes from this node over here, plus the max of its left and right subtrees, which we know are both 1, so we can take the max of 1 and 1. That's going to end up being 1, so the height of the overall tree is just going to be 1 plus 1, which is 2, right? So the height of this tree is going to be 2. We determined that pretty easily, and that's what we can return back up to this parent node, which is good for us, right? And from this tree on the left, the height is 1 because it's just a single node, so we return that up to the parent as well. So now from here, we know that the height of the left subtree is 1, the height of the right subtree is 2. We can take that difference, 2 minus 1, it's 1, which is less than or equal to 1. So that we do know that this is balanced from this node as well, right? And we can continue to recursively do that. If we had another parent node up above us somewhere, we could return, okay, the height of this overall tree is going to be 3, right? So that's the main logic we're going to follow. Yes, we're going to do this recursively, and there's many ways to code this up. The main way I'm going to code this up is actually by returning 2 values. I'm going to return a Boolean as the first value, which will be either true or false. Basically, for every single subtree, remember, we are going to determine, is that subtree balanced? We'll return a true or false for that. And the second value will be the height of that subtree. So from this subtree, what we would return is true because it is balanced, and the height we would return is 2, right? The height of this subtree is 2, so this is kind of what we would return. Now, if we ever, from any single subtree, if we ever return false, that means we found at least one subtree that's not balanced. If we find even one subtree that's not balanced, that means from the root, we're going to end up having to return false, which I'll show you how we can implement that in the code. It's pretty straightforward. Okay, so now let's get into the code, and main thing is we're going to do this recursively. Why can't I just use this outer function to do it? Because this outer function just returns a single value, right? The Boolean, but we actually want to implement this by returning 2 values. So I'm going to write a nested recursive function here, and we're going to pass in a single parameter, which is the root. And remember, this function is going to return a pair of values, a Boolean and the height of the tree. So first things first, the base case. If the root is null, right? This means that we have an empty tree. So is an empty tree considered balanced? Yeah, let's say it is. So for the first value, we'll return true in this case. And the second value, which is the height of the tree, an empty tree we can assume just has a height of 0, let's say. And now remember, before we determine from this root node, is this tree balanced? First, we want to determine if from the left subtree it is balanced and from the right subtree is it balanced. So let's call DFS recursively on the right and left subtrees and then assign it to the result variables left and right. So that's what we're doing with this single line of code, calling DFS on both subtrees. So now we want to know from the root node, is it balanced, right? How can we determine that? Well, we're going to have to take the absolute value of the left and right heights, right? So how can we do that? We can take absolute value left of index 1, because remember the second value is where the height happens to be, left of 1 minus right of 1. So this will give us that. So as long as this is less than or equal to 1, we can say that the tree is balanced, right? Not so fast, because remember, if either of these left or right subtrees ever returned false in the first parameter, then we know for sure that the entire tree is not balanced, right? So before we say that this condition is enough, we're going to add 2 more conditions. We're going to say, okay, as long as this is true, meaning that from the root it's balanced and the left and right subtrees were also balanced. So we can determine that by just taking the first subtrees were also balanced. So we can determine that by just taking, we're going to say, okay, as long as this is true, meaning that from the root it's balanced, and the left and right subtrees were also balanced. So we can determine that by just taking the the 0 index of left and the 0 index of right, and also this condition over here. Let me just reformat it slightly to make it a little bit more readable. This balance is what we're going to be returning as the first, as the 0th index. Let me just show you that. So we're going to return a pair of values. The first is going to be, is this tree balanced? And the second is going to be the height of the tree. How do we determine the height of the tree? Well, it's going to be 1. 1 comes from the root node that we're currently at, plus the max of the left and right subtree. So we can get that pretty easily. Left at index 1 and right at index 1. So whatever the max of those two is, plus 1 gives us the height. Hopefully this is pretty simple, but the balanced might not be. This balanced doesn't only mean is the tree balanced from the root position. This balanced means is the entire tree balanced at all. Because remember, if the left subtree, for example, was not balanced, then this conditional is going to evaluate to false, right? Because this balance is only going to be true if the left subtree was balanced and the right subtree was balanced, and from the root subtree are we balanced, right? So all three of those have to be true for us to return true as the balanced variable. Hopefully that makes sense, because that is the entire code. Once we're done with that, we can, in the outer function, we can go ahead and call our DFS starting from the root node. And remember, this DFS is going to return two variable or a pair of values, right? A Boolean and the height. So which of those do we want to return in the outer function? We want to return the Boolean, so we can return this at index 0, and then that'll be the entire code. So let me submit it to make sure that it works. As you can see on the left, it does work, and it's pretty efficient. So I hope that this was helpful. If it was,
you.